Good morning. I am Dr.S.Sharmila, Associate Professor and Head, Department of Industrial Biotechnology, Bharat Institute of Higher Education and Research. Today I am going to take unit operations and the topic is heat exchanger. And the content what we are going to discuss in this topic is heat exchanger. What is heat exchanger and what are the different types of heat exchanger? What is shell and heat exchanger? The definition of shell and heat exchanger, temperature profile of heat exchangers, then derivation for logarithmic mean temperature difference, then overall heat transfer coefficient derivation, and some problems on heat exchanger. Now, what is heat exchanger? So heat exchanger is an equipment which is used to transfer the heat from one fluid to the another fluid, which are separated by the solid boundary. So we can mainly classify this heat exchanger into two types: direct type of heat exchanger and indirect type of heat exchanger. And mainly, this is the main classification. Apart from this, we have more classification on this heat exchanger. So these are the various types of heat exchanger: shell and tip heat exchanger, double pipe heat exchanger, plate type heat exchanger. Then classification. So in this based on many criteria, the heat exchangers are classified. The first one is based on the nature of heat transfer process. Based on that, we can classify the heat exchanger as a recuperative heat exchanger and a regenerative heat exchanger. And second one is based on the terminal temperature difference of the fluids. In this, we can classify it into two types: mixing type, that is called direct type, and another one is non-mixing type. Non-mixing type can be otherwise called as closed type or indirect type of heat exchanger. And the third one is based on the nature of flow arrangements, how the fluids are flowing inside the heat exchanger. Based on that, we can classify into parallel flow, counter flow, cross flow, and mixed flow. These are the various types of flow which are followed or which are flowing in this in the heat exchanger, followed in this heat exchanger. And next is based on the number of passes, how many number of passes in the shell side and how many number of passes in the tube side. Based on that, we can classify it into a single pass and multi pass. And the next classification is based on the design. Based on the design aspect, we can classify the heat exchanger as shell and tip heat exchanger, plate type heat exchanger, then extended surface with fins, extended surface with fins, and double pipe heat exchanger. These are the based on the mechanical design. Based on the mechanical design, we can classify the heat exchanger into four different types. And the next is based on the physical state of the fluid. So through which the heat is exchanged or heat is transferred, or which or by which the heat is absorbed. So based on that, we can classify it into gas to gas heat exchanger, or gas to liquid heat transfer, or gas to coupling liquid, then gas to gas, and liquid to liquid. Mostly it will be followed in the it will be used in the oil coolers. And next is liquid or gas to condensing vapor. It is called condenser. That is also one of the type of heat exchanger. And the next is gas to boiling liquid, so which are called evaporators. So evaporator is also one of the type of heat exchanger. And the last one is based on the operating pressure range. Based on the operating pressure range, we can classify the heat exchanger as low pressure units, which is from 0 to 8 atmosphere, and medium pressure units, which is 8 to 35 atmosphere, and high pressure units, which are 35 atmosphere and above. So more than that, it can be classified as high pressure units of heat exchanger. Now let us discuss about shell and tube heat exchanger. Shell and tube heat exchangers are widely used in all the industries because we need to supply the heat. Mostly in industries, they will not be directly using the heat. So indirect type of heat exchanger will be mostly utilized in the process, because we cannot directly heat the material which are to be processed. So in that case, indirect type of heat exchangers, which are shell and heat exchanger, are used to transfer the heat from the liquid or steam to the processing liquid. Then the processing liquid will be sent to the process, thereby the heat transfer will be taking place and the reaction will be carried out and the production will be carried out. So among this, the shell and heat exchanger plays a vital role in the industries. And let us discuss about this elaborately. The shell and heat exchanger, it consists of the bundle of tubes. The bundle of tubes will be present, and these tubes will be fixed in the tube sheets. So more number of tubes will be fixed in the tube sheets, and this tube bundle will be placed in the cylindrical shell. There will be the cylindrical shell. Inside the cylindrical shell, this bundle of tubes will be inserted, and there will be the tube inlet and the outlet to supply the liquid, or so to supply the steam. There will be the, through the tube there will be the tube inlet, and so there will be the tube outlet. Similarly, there will be the shell inlet, and also the shell outlet will be provided at the other end. So this is the simple design, simple diagram of heat exchanger. Here these are called tubes. These are tubes, and these tubes are fixed in the tube sheet. This is tube sheet. In this tube sheet only, this tubes are fixed. So tubes are fixed in the tube sheet, and this is tube inlet. So here the tube inlet is provided. So the tube inlet is whatever the fluid is has to be passed into the tube, that will be passed through this tube inlet, and this is tube outlet. So, and here these tubes are fixed inside the cylindrical shell, and this is the shell inlet and the shell outlet. And these tubes are fixed in the tube sheet. There are two tube sheets. One is at this end, another one is another end. And inside the baffles are placed. So the baffles are placed to it will also provide support to the tubes. It will not allow the tubes to bend, because the distance is, if the distance is very long, then there will be the chance of bending of this tube. To avoid that, these baffles are provided. So the baffles are nothing but a circular plate, which is one side cut away, 1/4 of the baffle will be cut away, and it will be having number of holes in it. So this is the real-time heat exchanger, selective heat exchanger. Here you can see that this is a tube sheet, and this tube sheet is having a number of holes. In these holes only, the tubes are fixed. The tubes are fixed in the tube sheet, and this is baffle. So the baffles is also similar to this tube sheet, but 1/4 of the baffles will be cut away. Then only the fluid can be passed into this. The shell side fluid can be if it is entering in here, and since the baffles are cut away here, so that this shell side fluid can enter here, and it will take its diversion, and it will be flowing like this. So if you are increasing the baffles number of baffles, then we can increase the number of passes in the shell. Here there is it is a single pass, because we are not increasing the number of passes in the tube side. So whatever the tube side liquid is entering here, it will be passing only one time through this tube, and it will be entering to the outlet. And we can increase the number of passes in the tube side also by keeping the pass partition here. So the pass partition can be kept here, so that once the liquid, the tube side liquid entering here, it will be flowing through this pipe, and here it will be taking diversion. At that condition, here also we can keep one more pass partition here, so that it will be taking its direction. Again, it will be flowing in the next set of tubes. Then here it will come, and it will follow the another diversion. Then it will go to the tube outlet. So we can increase the number of passes in the shell side as well as in the tube side also. So if this shell side number of passes can be increased by the baffles. So the baffle will increase the uniform heat flow, as well as it will increase the number of passes in the shell side. In the tube pass partition, if it is provided in the tube side, then the number of passes in the tubes also can be increased. So what is the need of increasing the pass partition in the number of passes in the shell as well as in the tube? If the number of passes increased, then the resident time of the liquid will be increased, because here the resident time plays by very important role in the heat transfer. So if the resident time is increased, then the rate of heat transfer will also be increased. So to get more amount of heat transfer, the number of passes are increased. So this is tube bundles. These are called tube bundles are fixed in the tube sheets, and here we can see the baffles. And this is called shell inlet and the shell outlet are provided. And tube side inlets will be placed at this side. So here the tube side inlet and the tube side outlet will be provided. So steam will be passed through the nozzle into the shell side. Usually the steam will be passed into the shell side. And once the steam passes throughout this shell, it will be condensed because the heat from the steam is exchanged to the tube side liquid. So since the heat is transferred from the steam to the liquid, the steam will be condensed, and the condensed state will be withdrawn from the bottom of the shell side. If there is any non-condensable gases present at the startup or enter with inlet vapors are removed through the vent, and the fluid which has to be heated will be flowing through the tube inlet and can be withdrawn from the tube outlet. And these two fluids, the steam and this liquid which is going to be heated, are physically separated, but they are in thermal contact. And so here in this diagram, we can see this tube side one liquid will be flowing and outside the steam will be flowing. So there is no direct contact between the steam and the tube side liquid because there is the solid boundary, which is the tube boundary, tube wall is there. So it will not allow the steam and the liquid mixing of these two. So that's why it is called indirect type of heat exchanger. And the heat flows through the tube walls from the condensing vapor to the cooler fluid in the tubes. And this tube bundles, the number of tubes are called tube bundles. These are fixed in the tube sheets. And to promote the cross flow and raise the average velocity of shell side, the baffles are installed in the shell. So baffles are nothing but the circular disc of sheet metal with one side cut away. And these baffles are also perforated to receive the tubes. Then only the tubes can be inserted in the baffles also. And to minimize the leakage, the clearances between the baffles and shell and tube should be small. If the clearance between the baffles and shell is too large, then there will be the leakage. So to avoid that, this clearance should be very small. And these baffles, the baffles are guided, supported by the guide rods. And these tubes which are inserted in the tube sheets follow the triangular pitch or rectangular pitch, which is otherwise called as square pitch. First, what is pitches? The pitch is nothing but the center to center distance. The pitch is the center to center distance between the two tubes. And so here we can see the tube pitch. So these are tubes. Then this center of the one tube and the center of another tube, this distance is called tube pitch. The center to center distance between the two tubes are called tube pitch. And this there are many types of pitches are there. This pitch can be classified into square pitch, triangular pitch, and rotated square pitch, and triangular pitch with the cleaning links. So like that, many types, many arrangements of pitch, many arrangements of tubes are followed. So if the center to center distance between the two tubes so forms the square, then it is called square pitch. And if the center to center distance between the two tubes, three tubes, if it follows the triangle, then it is called triangular pitch. So there is some advantage as well as the disadvantage of these two pitches. In a square pitch, the cleaning will be very easy because the gap between the two tubes will be more, so that we can insert the brushes. Now we no need to dismantle the whole unit of this shell and tube. Just we can open the shell side and we can insert the brushes inside this two tubes, and it can be cleaned. But this is the advantage of that. But that is the disadvantage of this triangular pitch. In triangular pitch, we cannot clean it. We cannot we cannot insert the brushes into it because there will be more number of tubes. There will be more number of tubes will be fixed here. So since more number of tubes are fixed here, we cannot clean it very easily. We cannot clean. It is very so in this triangular pitch, the cleaning is very difficult. But in case of square pitch, the cleaning will be very easy. At the same time, the advantage of this triangular pitch is we can insert more number of tubes. So that is the advantage of this triangular pitch, but that is not possible in this square pitch because we cannot insert more number of tubes in the square pitch. That is the disadvantage of this square pitch. And let us see the temperature profile for this parallel flow as well as for a counter flow. So this is the temperature profile. So if you draw the graph between the temperature and the distance from the cold fluid inlet. So if you draw the temperature, then we'll be getting the curve like this. So this is the inlet of cold fluid and this is the outlet of cold fluid. So this is the direction of cold fluid flow. This is the direction of cold fluid flow. And since it is counter flow, the counter flow in the sense the fluid will be passing in the opposite direction. The fluid will be passing in opposite direction is called the counter flow. The fluids are flowing in the same way, same inlet and same side. Then it is called parallel flow. So here the fluids are supplying and are flowing in the opposite direction. That's why it is called the counter flow. So if in this counter flow, this side the hot fluid will be entering into this, and this is the outlet of hot fluid. So this is the direction of hot fluid flow. And the delta 1 is temperature difference at the inlet of cold fluid, and delta 2 is temperature difference at the outlet of cold fluid. Okay, so mostly counter flow will be followed in this heat exchanger in order to attain the more heat from the fluid. And here this is parallel flow. Parallel flow. In this parallel flow, so both the liquids will be flowing in the same direction. It will be so the inlet of the hot fluid as well as the inlet of the cold fluid will be at the same end. So the cold fluid will be flowing in this, and the hot fluid will be flowing in the same direction. So if you see the difference delta 1 and delta 2, that's delta 1 and delta 2 are the inlet temperature difference and the outlet temperature difference. So mostly, as I said, the parallel flow will be rarely used in the single pass exchanger because it is not possible to get the exit temperature of one of the liquid nearly to the entrance temperature of the other. So that is why mostly the counter flow will be used in this heat exchanger, and heat transfer is because of this, the heat transfer will be less in parallel flow than the counter flow. So always the counter flow is preferable in the heat exchanger. Then next is LMTD. So LMTD is the very much important one in the heat exchanger, and which is the logarithmic mean temperature difference. Here we are going to derive the LMTD equation. For that we are assuming that overall heat transfer coefficient, which is U, U is constant, and the specific heats, which is CP, the specific heat capacity of hot fluid as well as the cold fluids are constant, and the heat exchange with the atmosphere is negligible. That means there is no loss of heat. There is no loss of heat. So whatever the heat present in the steam will be transferred to the another liquid. It will not be transferred to the atmosphere. So we are assuming these three assumptions for deriving this LMTD, and this is the graph which is plotted between the heat flux and the temperature difference as well as the temperature. So this plot, in this plot we are getting the straight line is obtained so that we can find out the slope. The slope of this graph is d delta t by dq. The slope, if you see this, if you are taking this graph and if you plot the graph, this graph is a straight line, we are getting the straight line in this graph. And if you draw the slope for this graph, we'll be getting d delta t by q. This is the slope. So how can we define this LMTD? So LMTD is defined as the temperature difference, which if constant will give the same rate of heat transfer as actually occurs under variable conditions of temperature difference. So here d del T by dq is the slope. What is del T? Del T is nothing but the temperature difference, delta T1 and delta T2, inlet temperature difference and outlet temperature difference, which are delta T2 minus delta T1. And Qt is the rate of heat transfer in the entire heat exchanger. Q is rate of heat transfer. And we know that this dq by dA is equal to U into del T, which is already explained by the Fourier of the conduction. Here, instead of if it is a single liquid, then we'll be using the H heat transfer coefficient, since we have two liquids where the heat is transferred from one to another. So we are considering U. U is nothing but overall heat transfer coefficient. And after rearranging this equation, so if you are keeping the q dq in the left hand side and taking this dA to the right hand side, this equation will become u into delta t into dA. This is equation number 2. Now substituting equation 2 in equation 1. Equation 1 already we have here dq by d delta t by in this previous slide we already discussed d delta t by dq. So d delta t, instead of dq we are substituting this u into del t into dA. And again rearranging this one d delta t by and this whole thing is equal to delta t2 minus delta t1 by qt. And after rearranging this equation, we are getting the d delta t by del t. The term limits are delta t1 to delta t2. And if you are integrating this, also if you are integrating the area with respect to 0 to 8 AT, heat transfer area. And integration of delta t, d delta t by delta t is nothing but ln delta t. And after substituting the upper limit and lower limit, we'll be getting ln delta t2 by ln delta t1, which is equal to u into del t2 minus del t1 by qt. And integration of dA is a, and substituting the limit at. So we are getting the equation ln delta t2 by delta t1, which is equal to u into delta t2 minus delta t1 into at by qt. Now our aim is to find out this qt only. So qt is a rate of heat transfer, total rate of heat transfer. And after rearranging this equation, we'll be getting u into at delta t2 minus delta t1 by ln delta t2 by delta t1. This portion, this delta t2 minus delta t1 by ln delta t2 by delta t1 is called qt, which is delta tl. Delta tl is nothing but delta TL is nothing but logarithmic mean temperature difference. So this delta TL is logarithmic mean temperature difference, and the formula for this delta TL is delta T2 minus delta T1 by ln of delta T2 by delta T1. This is called logarithmic mean temperature difference. Next is the derivation of overall heat transfer coefficient. So we know that the heat transfer coefficient plays important role in the rate of heat transfer in the particular system. So normally for the rate of heat transfer for solid material, it will be we'll be using the thermal conductivity. Since here the heat is transferred between the two liquids, we are considering the heat transfer coefficients of the liquids, and the in between the boundary layer, the tube wall will be present. So the inside in the tube wall, the heat will be transferred by means of conduction, and again the heat will be transferred to the inside of the inside liquid, which is going inside the tube. So here convection and conduction process are taking place. So and many so convection, both modes of heat transfer will be taking place in the heat exchanger. And since liquid as well as the tube are present in this, there will be thermal conductivity. The tube will provide some resistance, and two liquids will provide resistance to the heat transfer. So there are many resistance will be offered by the liquid as well as by this tube wall. So we are considering since many resistance are provided, we are going to see how to find out this overall heat transfer coefficient. Okay. And this also applies to heat flow through the liquid layers and the solids in the series. So the formula for this overall heat transfer coefficient is generally dq by du is equal to u into del T. This del T is nothing but TH minus TC. I mean the temperature of hot fluid minus temperature of cold fluid, because the heat is transferred from this hot fluid to the cold fluid. And here the U is overall heat transfer coefficient. This overall heat transfer coefficient depends on so many variables. That overall heat that will be break into different parts, and considering the local overall heat transfer coefficient at a specific point in a double pipe heat exchanger. And here we are assuming the warm fluid is flowing through the inside of the pipe and the cold fluid is flowing through the annular space or outside of the pipe. And the second assumption is that Reynolds number of the two fluids are large to ensure the turbulent flow. Because in the turbulent flow only, the amount of the rate of heat transfer will be high in the turbulent flow. So we are assuming the Reynolds number is large to attain this turbulent flow. And both surface of the tubes inside of the tube as well as the outside of the tube are clear, that is free from the dirt or skin. And here the metal wall of the tubes tubes separates the warm fluid on the right side from the cold fluid on the left side. The change in temperature with the distance is TA, TB, TWH, TWC, TG. And the temperature profile is thus divided into three separate parts. One is through each of the two fluids and the other through the metal wall. In each fluid, there is a thin sublayer at the wall, a turbulent core occupying most of the cross section of the stream and the buffer zone between them. So here, this is the metal wall in the sense the tube wall, and inside the metal wall, the warm fluid is flowing, and outside the wall, the cold fluid is flowing. So the heat will transfer from this warm fluid to the cold fluid. Initially, the temperature of the warm fluid is considered as TH, and when it touches the tube wall, it is taken as TWH. And at the other side of the wall is TWC. And once it comes to this cold side, the cold side temperature is cold fluid temperature is taken as TC. Now, the overall heat transfer coefficient is constructed from the individual coefficients, and the rate of heat transfer through the wall is given by. So, in the wall, the rate of heat transfer is given by dq by dAl bar, because the tube is having inside area as well as the outside area. So, we are considering the AL bar. AL bar is average area, logarithmic mean area, which is equal to Km into TWH minus TWC by XW. TWH and TWC, the TWH and TWC are the wall temperature at the cold side and the wall temperature at the hot fluid flowing side. And this XW is the thickness of the wall, thickness of the tube wall. So after rearranging this equation, TWH minus TWC is equal to XW by Km dq by dAl bar. AL bar is logarithmic mean area, and Km is thermal conductivity of the wall, and XW is the wall thickness, and dq by dAl bar is the local heat flux based on the logarithmic mean of the inside and outside areas of the tube. And for liquid, we know that H is equal to dq by dA divided by T minus TW, and H is the individual heat transfer coefficient. And if it is inside a fluid, then we can take HI. HI is the heat transfer coefficient for the inside fluid, which is equal to dq. Since we are considering the inside heat transfer coefficient, we have to consider inside area. So HI is equal to dq by dAi divided by TW minus TWH. Similarly, for outside area, H naught is equal to dq by dA naught divided by TWC minus TC. This is for outside area. So these are HI and H naught, individual heat transfer coefficient for inside fluid and individual heat transfer coefficient for the outside fluid. And after rearranging this TWH and TWC will be getting the equations. TWC minus TC is equal to dq by dA naught by H naught is equal to 1 by H naught dq by dA naught. Similarly, TWH minus TWC is equal to dq by TW is equal to dq by dI. HI is equal to 1 by HI dq by dx. So these are the equations. And now we are going to add equation 1, 5 and 6. So TH minus TWH plus TWH minus TWC plus TWC minus TC. So which is equal to again the TWH plus TWH and minus TWH will be cancelled. Similarly, TWC plus TWC and minus TWC will be cancelled. So finally we'll be getting TH minus TC, which is the del T. So now what we have to do, we have to write down the equations for this TH minus TWH, TWH minus TWC, TWC minus TC. So that we'll be getting the del T value. So if we are substituting those equations, then dq is equal to 1 by dAi hi plus xw by km 1 by dal bar plus 1 by dA naught into h naught. This is the equation. Now we have to multiply and divide the equation by dA naught inside and outside. So dq by dA naught is equal to dA naught by dA hi plus xw by km dA naught by dal bar and dA naught by dA naught into h naught. So here dA naught and dA naught will be cancelled, and this dq by dA naught will be common. Inside dA naught by dA hi plus xw by km dA naught by dal bar, and since this is cancelled, we'll be having only 1 by h naught. And now we can take this dq by dA naught, which is common in this equation. We can take it to the left hand side and th minus tc to the right hand side, so that this whole term will come to the denominator. dq by dA hi plus xw dA naught by km into dl bar plus 1 by h naught. And we know that dq by d is equal to u into del t. This u is equal del t is nothing but th minus t. So u is equal to after substituting the rearranged equation, u is equal to dq by dA divided by th minus tc. If it is outside, if you are considering the heat transfer is based on the outside area, then this overall heat transfer coefficient u naught is equal to dq by dA naught divided by th minus tc. And our aim is to find out this dq by dA naught. So dq by dA naught is equal to this 1 by hi into d naught by dA, because in this previous slide we have dA naught by dAi. If we are differentiating this, integrating this, then we'll be substituting the area formula. So area formula, if you substitute, then will be the pi dl. That pi d will be cancelled, so that we'll be getting pi l will be cancelled. Only d naught and di will be there. So that only present here, d naught by di plus xw by km d naught by dl bar plus 1 by h naught. So 1 by u, if it is for based on the outside area, 1 by hi d naught by dA, xw by km d naught by dl bar plus 1 by h naught. And if it is based on the inside area, this inside will be changed into outside. So 1 by h naught and di by d naught plus xw by km di by dl bar, and here h naught is there, so 1 by h side. So this is the overall heat transfer coefficient based on the inner surface. And this is the resistance formula. We know that inverse of conduction is resistance. So inverse of coefficient is called resistance. And this is mainly we know since if it is a steady state conduction, del T by R is equal to del Ti by Ra and del T naught by R naught. So this can be written as del T by 1 by U naught is equal to del Ti by D naught by Di Hi, del Tw by Xw Km D naught by Dl bar. So this equation is mainly we have considered in the starting itself. We have assumed that there is no dirt or any other particle are present. It is free from the dirt. So we have already assumed it is clean. The tube is clean both inside and outside. If there is any fouling, if there is any dirt, then we are introducing the term fouling factors. So which is 1 by DAHD. So that has to be added in the starting itself. Then we have to do the same derivation. So that finally we'll be getting this overall heat transfer coefficient formula U0 for U0 and UI, that is overall heat transfer coefficient based on outer surface as well as the inner surface. So the U0 is equal to 1 by HDI D0 by DI plus D0 by DI HI plus XW by KM D0 by DL bar 1 by H0 plus 1 by HD. Similarly for inside area, heat transfer coefficient for inside area is UI and the formula is 1 by 1 HD naught di by d naught plus di by d naught h naught plus xw by km di by dl bar plus 1 by hi plus hdi. So this is the derivation of overall heat transfer coefficient. Let us discuss the problem. So methyl alcohol is flowing in the inner pipe of a double pipe exchanger. It is cooled with water flowing in the jacket. The inner pipe is made from 1 inch, 25 mm, schedule 40 steel pipe. The thermal conductivity of the steel is 26 BTU per degree Fahrenheit. And the individual coefficient and the fouling factors are given below. Calculate the overall heat transfer coefficient based on the area of the inner pipe. So we have to find out UI value. The diameter and wall thickness of 1 inch schedule 40 pipe is given. Diameter, inner diameter is 1.049 inch, D naught is 1.315 inch, XW is 0.133 inch. So here we can directly use the formula, and the heat transfer coefficient HI and H naught is given, and fouling factor is also given, HDI and HD naught is also given. So first thing, the diameter is given in the inches, so we have to convert it into feet, so that we are dividing it by 12. And we have to find out DL bar, because in the formula we have DL bar. So first we are finding out the DL bar. The formula is D naught minus DI by ln of D naught by DL. So first we have to find out the DL bar. Then directly we can substitute this value. All the values are being given in the problem itself. And since it is based on the inner surface, outer surface, we are using the formula, and all the values, if you have substituted all the values in the formula, then we'll be getting the overall heat transfer coefficient value. So this is the overall heat transfer coefficient value, which is 71.3 BTU per foot square R degree Fahrenheit.